Okay, so we're going to get started. Happy Halloween, everyone. Today we have Ian Dobbs-Dixon, who's our colleague from New York University's campus in Abu Dhabi. So Ian did both his undergrad and graduate studies at University of California at Santa Cruz, which is one of the smaller UC campuses, but it's always punched way above its weight in astrophysics. I don't know if Andrew's maybe not here, but I think Andrew did his PhD there as well.
Yeah, we overlap.
Oh yeah, okay, yeah. And then Ian went on to do postdocs in University of Washington and McGill, right? Yeah. Before moving to Abu Dhabi. So his work, as you'll hear, is mostly on various aspects related to exoplanets, which is, I'd say, one of the two really exciting topics in astrophysics these days, and there are many, but let's say two that are the hottest right now. So there's exoplanets and gravitational waves. Looking forward to
Great. Yeah, thanks for having me. Thanks for giving me the opportunity. Happy Halloween. So I'm going to talk about modeling atmospheres of short-period gaseous planets. Before I do that, I just want to toss out a plug a bit. For those of you who haven't visited us in Abu Dhabi, please come. We are a great growing department, physics department. There's lots of exciting research going on. In addition to that, we have two centers doing a lot of exciting astro-related stuff. There's the Center for Space Science, for which Srini is the PI here, which has been going on for several years now. And now we have the newly minted CAP3, or the Center for Astro, Particle, and Planetary Physics, which is literally about a month old. So new that we don't have a logo for it yet. So there's I should also mention there's actually some multiple postdocs in multiple areas of astrophysics associated with both those centers. So I encourage you to either apply and or spread the word around. So, like I say, it's beach weather there now, so come visit.
It's always beach weather there.
It's always it's too hot. Most of the times, in summertime, it's too hot to go to the beach. Okay, so it's a planetary talk, so we have the obligatory current state of the field slide. So as of now, yesterday, day before yesterday, it's about 3,200 confirmed planets and another 2,500 that are candidates, which are probably actually also candidates. Planets. So here's a plot of the separation versus planetary mass. As you can see, there's a huge range of parameters. And the color codes are based on how they're detected. So the vast majority these days now, of course, are done by the transit method, which is in red. Radial velocity, the traditional method, is in blue. These green points here in this kind of area here are microlensing, and then at very large separations, necessarily, of course, are these directly imaged exoplanets. So there's a huge amount of science you can do, of course, with this, and trying to understand the range and properties of all these objects is an exciting task.
Just for a very remedial question, the Earth and Jupiter masses is what?
Down here.
10 to the minus 3?
Yeah.
Or even below? Okay.
And back here. Yeah, so of course, detection thresholds, of course, moving down this over time. Okay, but I'm going to talk about atmospheres of hot Jupiter. So these are these guys here. And they are the best characterized of all the planets we know, just based on their proximity to the star, the size of the planet. So this not only are they the best characterized that we know now, but they will always be the best characterized that we know. For that reason, we'll concentrate on that, plus the reason I think they're kind of cool.
Is there a direct detection?
Yeah, I just saw that right there. I did not see
that
at all before. I did not know about that.
Yeah, maybe it's just a
Doesn't make any sense.
mistake in
I think it's a mistake.
exoplanets.org.
Yes. Don't understand how that would happen at all. Talking about atmospheric modeling, I think in general you can break it down in the field into two camps in terms of theoretical modeling of these things. There's forward modeling and then there's inverse modeling. So forward modeling is probably what you think most of you know. It's theory driven, and so the idea is you take as much physics as you can and you plug it into your model and you press go and you see what happens. The advantages of it are it's self-consistent, or mostly self-consistent, and the result that you get should hopefully give you some physical insight into the processes that are actually going on there. Disadvantages are it's incredibly computationally expensive, so at best all you can do is sort of a grid exploration of whatever parameters you put into your initial model. The inverse model takes a different...
Are there any models that include the interior of the planets in the modeling of the atmosphere?
There's models, of course, we include the interior flux. And one-dimensional models, you can do both. But in multi-dimensional models, you can't do both. So the inverse problem takes the other approach, and it's more of an observational driven. And what you do is you take a very simplistic parameterized model of your atmosphere, say. You do a robust, very detailed radiative transfer calculation, and you compare what you get to your observations in a statistical sense. And that allows you to move around in your parameter space in a statistical sense to get a thorough exploration of those parameters. So this gives you on the order of 10,000 models in the end. You have a family of models that fit your solution, fits your observation, and of course in the end you're also coming out with a robust estimate of uncertainties. So in my group, we work on both, and I think really what the most exciting stuff is going to happen is the interplay between these two things. So some of the stuff I'll talk about today. So just a brief overview, I'll talk a little bit about radiative-hydrodynamic models. Mine is called DRIFT, RHD, and that of course falls strongly into this camp. I'll discuss the basic atmospheric state. Okay, so we start to do radiation hydrodynamics, and then we start adding more and more physics on that. But we should first understand the basic atmospheric state. Yeah?
On average, how many free parameters do you have in your models?
In the hydro models? Jeez. Hundreds, right? I mean, everything hydro models.
You said 100?
Yeah, 100. Hydro models are everything from resolution to, everything.
So when you say you grid those models, you're not gridding all 100 parameters?
No, and that's exactly the problem, is that there's no way you can do that. You can say, all right, let's explore an interior flux or something like that, or try to pick something that is what you hope is physically relevant to explore. That's how
But
you can get.
give us an example of 10. I mean, how can there be hundreds?
So,
And have the model be tractable?
so it's like the resolution and all.
No, but that's not a parameter of the model. It's not a physical parameter.
Oh, no, okay.
I
Well,
think you were asking about physical parameters, like abundances of different metals.
Yeah, okay. So, sorry, yes, those are two, that's a good point. There are two separate, but there's the computational parameters, which unfortunately are very important. And then there's physical parameters. So physical parameters on the order of 20. So composition. Is the gas in thermal equilibrium? What is the irradiation temperature? What is the albedo? What is the interior flux? All these things are physical parameters. Okay, so once we do the basic atmospheric state, I'm going to talk a little bit about adding some physics, in particular cloud modeling in these models, in these forward-driven models. But then I want to switch to retrievals. And so retrievals are what we know as these inverse models. So we retrieve the state of the atmosphere. And so first I'll talk a little bit about the validity of what we use in the field, which are one-dimensional retrieval models. And then try to use, like I say, try to use insights from this side to inform what's going on that side. So I'd like to present this kind of multi-dimensional retrieval model that we've developed. And then finally, if you have time, we'll talk a little bit about, again, taking what we've learned from the cloud modeling in multi-dimensions and applying it to retrievals.
Could I ask just again a naive question? So this observation-driven bullet point, I mean, this is really for exoplanets? Because for exoplanets, there's how much information is there for
Yeah, there's not very much information.
Very much, right?
Yeah, so yeah, we're data star for sure. Yeah, we're in here, we're data stars. So, but this is fine. You can still constrain models. So basically, this parameterization is a parameterization of the PT, the pressure temperature profile, for example. And from that, you make some assumptions of the abundances and things like that. And then you do detailed radiative transfer, come up with a spectrum. And you compare that spectrum then appropriately to the observations and figure out some direction to walk in MCMC and come up with a new set of parameters and rinse and repeat 10,000 times. So yes, absolutely, we're starved for data. And in fact, this is an important point, is that these models that we have right now do a reasonable job with the data that we have on hand. But with the kind of the advent of JWST era, we need a whole new paradigm for understanding how these things interact and evolve.
How much do the atmospheres of our planets inform these models?
Our planets?
Yeah.
So the ones we'll talk about now, it would be Jupiter. But Jupiter is significantly different than these planets in the sense that it doesn't receive that much light from the sun.
But these models do well on Jupiter or not?
These models do, yeah.
They do well on
They
Jupiter.
reproduce the zonal jets. These kind of
Yeah.
So
behavior.
the data that you're trying to fit is, for example, a spectrum, and do you have like some information from timing on the atmosphere and things like, like.
Yeah, definitely. And I'll show you
Oh, you're
the
gonna show us,
examples
okay.
of the observations. Exactly. Okay, so this is basically it. The fundamental, or there's a hierarchy of models, of course, in the community. But I'd say the state of the art is three-dimensional Navier-Stokes equations, coupled to two-stream radiative transfer using correlated K opacities for those of you who do radiation transfer. So these are all the equations in all their glory. So you, of course, the continuity equation, an energy equation here with your advection term, of course, very important. And then various other terms. Here's your divergence in the radiative flux. That's how it feeds back into the energy equation. And then the momentum equation here, again, advection, so on and so forth. This is solved in a rotating frame, which is informed by the fact that we think that these planets are tidally locked to their host star. So that means that the rotation frequency and the orbital frequency are the same. So one side of the planet continually faces the star. So this is like our Earth-Moon system. Okay? And has a very important implications for the dynamics. And then, of course, here you have the upwelling radiative flux and downwelling radiative flux.
Do you assume that because the planets are close to their stars, or?
The tidal locking, theoretical, tidal, we don't have any observational evidence, but theoretical tidal locking timescale is on the order of 10 million years. Incredibly fast, because they're so close. Yeah.
Because they're so close.
Yeah,
right?
so these are planets that are orbiting about every 3 days.
Okay.
So in several stellar radii of their host stars.
Does that extend down to the core?
Does the radiation extend down?
I mean, no, the
Tidal
phase
locking.
lock, tidal locking.
That's a good question. No one knows. Yeah.
And presumably
Does it- yeah,
they're
exactly.
terrestrial objects, so maybe they are locked.
At a certain point, it becomes convective in the interior, of course, but are they rotating as a solid body? I don't think that's understood at all. So I will talk a little bit again eventually about adding physics on top of this kind of radiative convective pillars. But I think it's important to note that there are still very many important questions involving just radiation and hydrodynamics by themselves that are still outstanding questions that people are working on. Just to kind of give you a flavor for why radiation is important, we were talking about Jupiter there for a second. The interior flux from Jupiter is about equal to the flux it receives from its host, the sun. Okay, so those are about equal. In hot Jupiters, the flux they receive from their star is 5 orders of magnitude higher than its interior. So it's completely dominated in the outer regions by the flux from the sun. Okay, so here's a kind of a snapshot of a simulation. So temperature on the left, zonal velocities, that's zonal around the planet, velocity on the right. And these are snapshots of constant pressure surfaces. So just concentrating on one of here, this is longitude. Okay, this is latitude here. So this is the North Pole, the South Pole. The equator runs through the middle. And this is longitude, excuse me, I almost mix those up. And the 0, 0 point right here is the substellar point. So this is the point that perpetually faces towards the host star. And the night side here, given back here.
Sorry.
Yeah, okay.
Sorry. But this energy balance between what you receive from the star and what you receive from the core, what is it for the Earth?
1370 watts. I mean, what is it for the Earth?
We receive much more.
Yeah, we receive much more from the
sun,
yeah, from the
by
sun.
like several orders of magnitude.
Yes, I would say.
Yeah.
Yeah. Okay. I know it's 1370 per watts
square
per
meter.
meter square for from the sun, but I don't know what the interior.
I'm sorry, I didn't see, you didn't have magnetic field or something?
No,
like that.
yeah, no. Magnetic fields really in the field have not yet been introduced. So anyway, you see multiple interesting features here right away. You see a big contrast between day side and night side, which is understandable. You're heating on this side, and this side never receives any stellar radiation. But it's interesting, this is not cold, 100% cold. And so this is actually being heated by what you can see is this jet here. So this jet, which here is in kilometers per second, so this is 5.8 kilometers per second, so it's like a Mach 1.5 wind. So the supersonic jet encircling the planet is ejecting energy from the day side to night side. So that's heating this area up here, especially up high in the atmosphere. And then the other thing you can see is the hottest point on the planet is not located at the substellar point. So again, the substellar point is here, or say for here. The hottest point is here. It's effectively downwind. So it's been ejected downwind. The energy being ejected downwind. So the hottest point is offset somewhat. So I do just want to point out this jet feature, because we're going to come back to this, but quite important. So you see there is some structure here, but it is fairly uniform across the entire planet. So we'll come back to that.
And
What is the temperature difference? I can't tell.
This is okay. So this is a function of pressure: 10 to the minus 4, 3, 2, 1, and 1 bar. So say here, this is about the coldest kind of vortex regions you get down here, a couple 400 degrees, and this would be 1100. If there was no advection, this would be on the order of 100 degrees on the backside, just based on its interior heat flux.
And can you? It's always confused me that this flow goes one way. Can you tell us which way that is, and do you have any intuition for it?
Yeah, it's and this is one of the examples of problems that are still just dealing with radiation and hydrodynamics that are
Exactly,
still
yeah.
outstanding. We have some idea. We published one paper, and another group has published another paper on this. So in principle, you're heating the day side and you're cooling the night side. So there should be flow. There's a pressure gradient, so there should be flow. The question is, what breaks the symmetry? Why does it start super rotating? So this is an angular momentum maximum, right? Which should not be there, right? It should be degrading away. So something is actually pumping eddies there. So what happens is actually, we think, is there are waves generated by this day-night pressure temperature differential, which are generated. So Rossby waves and Kelvin waves. And it so happens that there's an offset in how those waves are, so that it basically develops these permanent eddies which pump angular momentum into the jet core, maintaining them.
Do you have Rossby waves and Kelvin waves in your simulations?
Yeah, that's well, we extracted those basically and showed that they're existing in our simulations.
But I mean, you don't make any assumptions. This is what happens in your core, is that right?
Yeah, so that's right.
Yeah, you
So
just
it's
turn
like-
on the
it's
machine
like
and
Venus.
Stuff
you
as much
get
physics in there as possible. And
It's like Venus then,
it's like Venus.
super rotating.
Yeah.
Atmosphere.
Okay, so back to observations that you asked about, Glennis. So what we'd like to do now is observe these. And so there are three classes of observations, really. There's what happens is called the transit, primary transit, when the planet goes in front of the star. What you can do is you can basically observe the stellar light as it transits through the limb of the star. At different wavelengths, it's going to be absorbed at different locations, and so you can get an absorption spectrum, basically, out of it. So that's one. The other is, so you can see as it goes to the day side, you're interested in what is the spectrum from the day side, the emission spectrum from the day side. And to get that, you basically take a spectrum in this state right here, where you see star and planet. You wait a little bit until the planet is hidden, and you subtract the two, and that's the stellar, that's the planetary spectrum. So that's transit, emission, and then of course you can do this as a function of phase. And so because this thing's tidally locked, you're going to see different fractions of the day and night sides as the planet orbits its star. So those are the three kind of classes of observations. So those are done, of course, by real observations. You know, what I do is I go and I observe my planet. So I run these simulations, and then I post-process by basically doing ray tracing through the atmosphere, and you come up with observation predictions that you can compare to real observations. So I'm going to concentrate for now on this transit, so this one here. Okay. And this essentially gives you the planetary radius as a function of wavelength. So here's 1 micron, 10 microns. And in black is the model prediction. And so you see these features here, which are basically due to water absorption primarily, although there's also CH4 and CO in there. And you see this strong scattering slope here. And this red is the actual data from the various instruments and various people. So that's all good. We seem like it works pretty well. The caveat was that I had to put in an extra opacity. So most, when I talk about this, water and such, this is molecular opacity. That's all built into the code. What I had to do here to match was I had to put an extra opacity, which was a gray component, I have wavelength independent, and then a strongly scattering, Rossby, say a Rayleigh scattering component. And that was the only way I got this to match, and also the level of here. If they hadn't had this gray opacity here, these troughs would be off the page. So this is meant to emulate the effect of clouds. Okay? So clouds, it turns out, are quite important. So this is a plot from a few years ago, but it's still a good illustration of a whole series of hot Jupiters that seem to make transition from relatively clear atmospheres up here, where you see strong molecular features, to relatively cloudy ones here. We have strong optical slopes and really muted atmospheric feature, or sorry, molecular features. So there seems to be a range of planetary properties or cloud properties, but nonetheless, they're incredibly important.
I'm a little confused because some stuff looks like a spectrum, and then there are what look like data points.
Those are data points.
But so what's the spectrum part? Your
So
prediction?
that's not mine, but these are
Somebody's
one-dimensional
prediction.
models. Yeah, somebody's. Yeah.
Really, all we know are the data points.
Yes. Yeah. So these are right. These are the best fit models basically for this group.
These models that you use, is that a family of models the whole community uses, or are they built by you?
The ones that I'm going to talk about were built by me, but these guys are another group. These are one-dimensional models. They're not multi-dimensional models. But there are now, I say, 4 groups in the world that are working on kind of the multi-dimensional radiative hydrodynamics. So, which is great now because we have this hierarchy of models, and we have different assumptions and different codes, and comparing and contrasting is finally being able to happen. Okay, so important note about clouds. When you say clouds, everyone thinks this. Okay, it's not that. I think it's more important to think in terms of a haze. So this is LA on a particularly pleasant day. Like haze layer here. It's the same thing that's going on actually on Titan. So this was a real observation by Titan with Cassini. So what they did was actually looked at a stellar occultation of Titan from Cassini, and they were able to take basically that same thing, that transit spectra. And indeed, again, without this haze, additional haze, these absorption troughs would be off the page. So think haze, don't think fluffy clouds. Not only that, of course, clouds aren't water.
Why does adding haze make less absorption? Or are you saying that the whole thing would be shifted, but then the troughs would be deeper relative to the peaks? Or
so the lower this is, the farther into the atmosphere you're probing. So the more transparent the atmosphere is.
okay.
So you go down here.
Effective transit.
It seems like the radius is smaller.
All right.
So can you tell if the haze goes close? And I guess these that don't have surfaces, these are,
Jupiter's?
hot Jupiters.
Yeah.
But can you say anything on kind of where they are in the atmosphere, where the haze is? If it's
Yeah, so
there
that's what
or-
we want to calculate now. Basically, where do they come? And so the history of this field really comes from one-dimensional models of brown dwarfs. Okay, so this is a rather old plot, but what you'd expect, or what kind of condensable species you'd expect, is a function of planetary atmospheres. Okay, so hot Jupiters are operating in this kind of area here. So the clouds we're talking about are silicate clouds, or magnesium clouds, or even iron clouds. Okay, so very much not the puffy clouds you think about today. So as you can see, I've kind of listed several things here, just several, not all, not an exhaustive list, but they affect the transport of radiation, they change the atmospheric chemistry, obviously that therefore changes the dynamics. It changes the detectability of, say, water in the atmosphere because you obscure features. You can block stellar light, or you can increase albedo, and so on and so forth. So there's quite a bit of physics that goes into this. So brown dwarfs, of course, are fully convective. So a one-dimensional model does a good job. I think hopefully I've convinced you from the plots of temperature, for example. Hot Jupiters are not spherically symmetric in the least. So you really need a 3-dimensional cloud model. So what we did is we coupled a microphysical model developed for brown dwarfs to the global climate models. And here's kind of a cartoon picture of what goes on in cloud formation in hot Jupiters. So the stars, the stellar lights come from this side, so you have a hot day side and a cold night side. You have some formation of nuclei high in the atmosphere, say, and then as that is transported via advection, via strong jet, to the night side, it gets cool enough where all of a sudden stuff can start condensing on the surface of those grains. And so that grain grows larger and larger as it transported along. But at a certain point, whatever is condensing onto the grain runs out. You deplete, say, the oxygen that you're condensing. And so that kind of gets you to a point where you come into equilibrium. But you continue along around the planet, at a certain point you reach the day side again, where the material evaporates, it goes back into the gaseous form, and then the cycle repeats. So it's this kind of the structure where you'd expect clouds to be predominantly on the night side of the planet, where it's cool enough to condense.
The internal ellipse is the planet.
Yeah, this is an annulus of the planet. So this would be maybe 100 bars to 10 to the minus 5 bars. Okay, that's the cartoon picture. In detail, what we actually do is we solve 4 moments of the particle distribution. So these moments, ratios of various moments, give you things like this, the radius of the particle, and so on and so forth. But if you look at it, it's basically it's a fluid dynamics equation, right? So this is a change of the element. This is an advection, 3-dimensional velocity, and then if that particular element nucleates, you have to include that. And then here you have basically a term which is a source or a sink. Basically, are you evaporating or are you condensing? As I mentioned, it's not just the grain you have to track. You actually have to track what is condensing onto the grain and is it depleted. And so again, you have an additional conservation equation for each element that you're tracking. And again, it looks like a fluid dynamics equation. You have an advection here of this epsilon. You have some nucleation term. And again, this is a term that will either be positive or negative depending on whether it's growing or whether it's evaporating or it's condensing.
L is what? Some concentration of something like what is L?
It's a moment of the particle distribution. So in the end, again, what we have for we take those, and what we've decided to do for the simulations that I showed you is the nuclei we assume are going to be titanium oxide. This is taken basically from the brown dwarf community. That's what they use as their nucleation sites. And then there's 5 cloud formation species that we're going to follow. This 2 titanium silicon oxides and some magnesium silicate oxides. And so in order to track that, we also have to track 4 elements, right, that go into making those. Now, in reality, there's probably much more. We had to make some choices in terms of computation. And these seem to be the most dominant ones that we're going to pop out. So you're left with 4 moments, 5 volume equations, following 4 elements. So that's the cloud model. That's the green box here. Okay. Now, you form clouds at a certain location, and at every given location, you know what the cloud is. And so using knee theory, you can calculate what the opacity is based on that. And that could be fed back into your radiation module to change how the radiation flows. As you change how the radiation flows, you change the energy distribution, which of course changes the hydrodynamics, which changes how the clouds are redistributed. Okay? So you can see this very coupled, very interconnected system.
So kind of going back, so
Yeah.
You talked, briefly that it's, I'm sure, computationally expensive. So can you give us a sense how long it would take to run one set, and then can you run kind of explore the whole parameter space? Or
Yeah, so it took up on the order of 4 weeks to do a simulation that we seem to come to kind of equilibrium. And we weren't able to do basically an exhaustive.
We're able to do what?
We weren't able to do a large parameters search. Right.
So 4 or 5 weeks depends on which computer you use.
Sure. But, so on Dalma in
Okay.
Abu Dhabi, which is a fairly good computer. Okay, so let's see if it actually works. That's our kind of idea. Here we go. Okay, so here's 4 plots. This is the equator again. So these are isobaric pressure surfaces. So this is temperature. This is the day side, right? So this is the substellar point. This is the hot day side and the cool night side. So what's happening? So let's look in particular at this particular species, silicon oxide. Okay. And here I'm plotting the volume fraction. So how much of the grain is in silicon oxide? So on the day side, it's basically 0. Okay. But as you move to the night side, you pass this critical terminator. The temperatures drop low enough so that this silicon oxide starts to condense onto these grains. Okay.
These are SiO2 molecules that you're condensing?
These are grains. This is
Well, onto the grain, but
the nucleation site is a TiO2. Titanium oxide.
you're condensing the molecule as a whole molecule, or you're forming SiO.
So there's O2 that you have to track as well.
So they're all SiO2 molecules in the gas phase.
Yeah.
Okay.
Why pick these particular elements? Just for
Yeah. So like, if you did a one-dimensional model, you'll be able to follow, 20 or 30 different ones. But we had to make some choices, computational choices, basically. And so based on one-dimensional models, these seem to be the most prevalent. Okay, so these start to grow. And over here you can see this is particle size. So very small, very relatively large. And so again, as we're following the same story, on the day side it's hot, they remain small. But as soon as you hit this point, they start to grow larger and larger. And you can see the silicon oxide is starting to increase. But at a certain point it saturates, it doesn't keep growing. And it's precisely here because this is a silicon in gaseous form. Okay? So at a certain point you run out of silicon. So you can't keep growing that if you don't have the gas. And so you get to that point, come around, and again, once you get to the day side, you start evaporating. The gas goes back into silicon form, the silicon goes back into gas form, the particle size comes down, and then it repeats.
Well, it's silicon in the gas, not silicon oxide.
It's, yeah, we track silicon and oxygen, sorry.
And they both, I think you have.
Yeah,
some-
you have to figure out the reaction rates of sorry, I misunderstood your question. So, again, there's many plots here I can show you, but oh, I should say, like again, the dominant mixing here is in the horizontal direction, right, or the longitudinal direction. Whereas previous models, brown dwarf models, the only mixing really is happening in the vertical direction. Mixing does happen in the vertical direction here, but it's by far less dominant.
These are equatorial slices?
These are equatorial slices, yeah. Yeah, and it's completely, as you can see here, it's very three-dimensional. Well, you can't see, it's very three-dimensional, it's very complicated. This is TiO2, SiO, SiO2. These are the 5 species that we're looking at. And you can see, again, these are volume fractions. So the grain is basically 100%, 96, 100% TiO here. But at backside, there's basically none of it. Because there's the SiO2 SiO becomes prevalent on the upper atmosphere, SiO2 in the lower atmosphere, and so on and so forth. So the point is, they're incredibly not spherically symmetric, and very, where you are on the planet matters a lot in terms of what your cloud species is. So that's great. So does it work? So do the same thing, and we calculate theoretical spectra. And so here I'm showing 2 theoretical spectra. This one is the day side emission. So this is emission spectrum from the day side of the planet. The black is the model, and the data, various groups and various instruments is shown in the various colors. This is, again, the transmission spectra. Again, the black is the model, and the dots are the various observations. So I'd say for emission spectra, we do fairly well. Not great, but fairly well. And at the longer wavelengths, we do fairly well for the transmission spectra. This slope here is significantly less than before because I don't have that parameterized model in anymore. So we're missing the slope significantly here. And there's several explanations for that. Probably the best one is that there's probably a population of very small particles really high in the atmosphere, like at 10 to the minus 10 bars, so much higher than we can simulate. And that's causing that steep slope.
What exactly is theoretical here?
These are, so I've run the hydro models,
Yes.
and then I've generated spectra, run basically the ray tracing through them to figure out what emission or transmission spectra would be.
And that's model results, right?
Yeah, so
What's the difference between them and these dots you
the
have?
dots are the data, the real data.
So I think you maybe already mentioned it, and I missed it because I was thinking so hard about it. So it's raining sand on these planets,
Yeah.
and but the sand and like the silicides and like you said, there's corundum. That stuff doesn't all form like a solid rocky planet.
No, it doesn't sink. I mean, there's still, so I said most of the mixing is in the horizontal or the longitudinal sense. But there is mixing in the vertical direction. Okay, so as you sink, of course, you're going to get hotter and hotter and hotter, and at a certain point it evaporates, and eddies will mix that material back up into the atmosphere, similar to like the bottom of a cloud bank on Earth. So, first of all, there's not nearly enough. These are all very minor constituents.
But on Earth we have oceans, so which suggests that the clouds do settle out into the center.
Sure.
And so here the oceans would be sand and other grits and grains.
But I think once you grow a grain of significant size, it's gonna sink.
Yeah.
And instead of hitting a solid surface like it does on the Earth and stopping,
Well,
it's going to continue going until it gets hot enough that it evaporates.
Oh.
So do you these don't have these are not rocky planets.
No, I understand. The question I'm asking is why doesn't it become a rocky planet if it's always raining solid bits of grit?
Yeah, so if the temperature continuously increased and if that water molecule was able to continue to fall, then eventually it would evaporate.
In the simulations, what boundary condition do you put at that little circle?
The inner one?
Yeah.
So you assume some interior flux, which is coming out. So you go to a planet, basically a structure model, one-dimensional structure model, which you basically modify the interior entropy such you match the radius of the planet. Okay, and then that gives you at a given location what the temperature is and what the temperature gradient is, which gives you the flux.
I'm taking you back 2 slides or so before. What kind of nucleation models do you have? Is this homogeneous nucleation of some sort?
No, I mean, it's not. It's homogeneous. Yes, it's homogeneous nucleation.
Yeah.
But it's
Although it settles on some other molecule, yeah. Okay.
Yeah, so the nucleation is this TIO model.
Yeah.
Now, there are other people who claim sulfur components that are more dominant in the planet. But again, I'm working with brown dwarf people, and so these are the type of models they use. It doesn't seem to be too prevalent. It's really easy to form these seeds. It doesn't seem to be too relevant. It's really easy to form some sort of seed. And once you form that, they can start to
Yeah, I'm
condense.
surprised it's
Green cells.
Okay, so those are the forward models. So I wanted to kind of shift gears here and ask, I just told you that we just ran 1 or 2 of these models, generate the spectrum, they kind of match, but how close are we? So for that, we really want to, again, turn to this interplay between forward models and inverse models. And we ask, how well do the atmosphere structure, how well does it actually work? How well do retrieval calculations work? So we've done this, but how degenerate was my solution, right? If I had changed my parameters a bit, maybe I could have gotten a similar solution. So again, we want to use inverse models, but I think first we actually really need to ask, do we believe the current generation of retrievals are inverse models? And the real issue is that these retrieval models are one-dimensional. One-dimensional models, and I just showed you in so many ways how these planets are not one-dimensional. So we're going to concentrate on the day side. And so I thought maybe I should tell you a little bit more about, in detail, what a retrieval model does. We're using 2 retrieval frameworks. One is called BART, which is Bayesian atmospheric radiative transfer. And then there's a kind of a daughter of BART, which is Pirate Bay, which is a new and improved one. So it consists of basically 3 self-sufficient modules. You can use them for other physics if you want. There's a thermochemical equilibrium abundance module, there's an MCMC model, and then there's a radiative transfer model. And so here's how this works. You take some initial guess. Remember, we're parameterizing, and I'll get to the second. We're parameterizing the TP profile to some incredible simplistic way. So we get 6 parameters, or 4 parameters, which designate the TP profile. So we take a guess at those 4 parameters. We generate an atmosphere, a PT. We run a detailed, line-by-line radiative transfer calculation that generates a spectrum. We then integrate that spectrum however we want based on the instruments we want to compare it to. And then we compare that, the model and the observations, and then use the MCMC to walk through the parameter space and generate another atmospheric model based on that. And you run around this thing 10,000 times exploring parameter space, and eventually you pop out with some best fit or a series or a family of best fit solutions. So again, the goal overall here is to estimate the model parameters as well as their uncertainties. So this is the model we use. There are, I think, probably about 10 to 15 now that are in the community, and they all operate on the basic same principle. This temperature scheme is important, and again, there's basically 2 models that are used in the literature these days. One is based on Madhu and Seeger, 2009, and it basically breaks the atmosphere into 3 layers. Again, you want these to be incredibly simplistic. You just break it into 3 layers, 1, 2, 3, and specify these parameters, which will give you basically pressure temperature curves in each of those layers. So that's one value. It's, like I said, incredibly simplistic. But then over here is one based on some work by Guillot, which is more based in the actual radiative transfer equation. And here, again, you come into something like this, which leads you to a set of 4 opacity. That's 4 parameters to generate this. And these plots are basically try to illustrate how all the different variety of pressure temperature profiles you could get by varying these various parameters. Okay, so I vary one and keep the other constant. How does the temperature pressure profile change? So what we did is we want to ask, does the retrieval framework actually work? And to be able to answer that, we actually need a real planet. We need to know a planet, what the temperature pressure profile of a planet is. So what we decided to do is use the GCM models as the real planet to observe. So we took these high resolution, took these 3-dimensional radiation hydrodynamic models, we generated high resolution spectra, and then we used those as the input into the retrieval calculation, and compared the results to what we get actually, to what we put in. Okay, so here, for example, is the high resolution. The green is the high resolution spectra from the GCM model. Okay, and here is the pressure temperature. Here's a bunch of curves. These are all the pressure temperature curves that actually the light lines that actually exist in the planet. And the best fit model was this. What was that? This is not what I wanted. Anyway, the best fit model comes through like this, something like this.
Best fit
So it's on the next. Yeah, it's on the next one here. Oops. There we go.
By best fit, you mean whatever fits this data best?
Yeah, exactly. So this is the retrieved profile. Okay. Yeah. So again, pressure and temperature. The dotted lines are the actual pressure temperature profiles on the day side of the planet, and the retrieved one is the black. Okay. The retrieved here is black. Don't worry about this right here. You can't trust anything down here. Because you're basically not getting any light from down there, so there's no reason you should get any information down there. But the point is, this black profile is the best fit profile. It doesn't exist anywhere on the planet. Okay? Now we tried to compare it to various things like the mu weighted, where the mu is the cosine of the angle from the substellar point, straight means, and so on and so forth. None of it seemed to work. So these retrieve models are great, but it's important to note that you're not actually retrieving anything that physically exists on the planet. And the real reason is, again, these planets are not one-dimensional. So the next step.
So why do you say it's great?
What?
You said it's great?
I'm being political. I guess you guys are planetary people, especially.
This is some hypothetical mean.
So the next step is to do, for example, phase-dependent retrieval. Okay, so do retrieval every time at a bunch of different orbital phases. And so that was the first step. And so indeed, that's what we did. So this is when orbital phase is 0, is when you're looking at the night side. And these are the family of models. You know, 1 and 2 sigma contours, and the best fit model is black. And so you see, as you go from orbital phase of 0 to halfway across the orbit, indeed, you get hotter and hotter, and then cooler and cooler, as you would expect. So this is for the planet HD 43b. It's a hot Jupiter, and this is using that same method I described, but using the Spark MIT GCM. So that's great, and it seems to work. But again, it's pointed to the fact that these are not spherically symmetric. And you also did one important thing. You retrieved all of these spectra independently. So this spectra has no information about that spectra. You don't care what happened here when you're retrieving here. But that's losing some fundamental quantity, and that's the jet. The jet is a unifying feature that links all the different phases.
You mean you have data for all these phases?
Yeah.
That's amazing.
Yeah. Yeah, so I mean, this one is a very highly observed planet. And so they've looked at the phase curve, spectrally resolved phase curve. Again, the data is somewhat ratty, but so the next step here to go beyond this is to develop a phase curve which simultaneously somehow links these and simultaneously retrieves the entire planet.
Can I ask about that last question? I mean, how do you, probably not understanding something basic here, but I mean, so this thing is phase locked.
Yep.
And you're looking at light from the star passes through the atmosphere. So how do you see all these different phases? Don't you only get to
No,
see-
this is emission spectra. So you can run a retrieval on any type of data you want.
It's not absorption. Okay.
Yeah. So this, yeah, sorry, I should have said that. Yeah. That's emission spectra. So you're seeing the different fractions of day and night side as you.
But still, the day side is when it's on the others. Oh, okay. But I guess the orbit is inclined to the. Okay. So you.
The day, so you don't actually see 0.5. You see 0.52 when it's just before it goes behind the star and right. You know. Yeah. So what we want to do is to develop two-dimensional parameterization. Okay. That fundamentally links different phases via the jets. So to understand how a model like this could work, let's go back a little bit and understand how to develop a 2D radiative solution. Okay? And so it's actually fairly straightforward. What you do is you start with radiative equilibrium. Okay? So the emission and the absorption are exactly balanced at every given location in the atmosphere. And then you use the radiation moments, and you use closure relations and boundary conditions to basically calculate the temperature as a function of position in the atmosphere. So this is the temperature throughout the atmosphere. So total temperature, it's a function of longitude, which is basically encapsulated in this mu parameter, and optical depth, which is depth in the atmosphere. So you have two components here. You have a component that's associated with the internal energy coming out from the inside, and you have a component here which is proportional to the irradiation temperature, how much energy it's receiving from the star. So in the upper regions, this dominates, and as you get down to 100 bars, this becomes dominant. So if you do that,
So you need to go down to 100 bars to explain what they see in emission from
no,
microbars?
no. Well, I guess my point was this: up in the upper atmosphere, this is basically negative. So this is a plot of that calculation. So again, an equatorial slice. Here in temperature and pressure. So the substellar point right here has this kind of profile like this. It's the radiative equilibrium solution. And then as you move around in longitude, you move profiles here and here and here until you hit this key point, which is 90 degrees, or the terminator, and that's that profile. And then there's no difference between profiles all the way across here because there's no irradiation. So that's step one. So what we want to do is modify that to add in jets.
How many phases did you have in order to get these data?
That particular one,
Yeah.
or the
Yeah, for this particular thing.
this one. Sorry, this one. Are you talking about this one?
About 6, yeah, okay, fine.
Okay, so we want to include advection. We need to do only one simple modification. Instead of being a 0 here, right? So instead of emission balancing absorption exactly, we have emission and balancing absorption with the added effect of horizontal energy or sink. Energy sink or gain based on advection. Okay? So in radiative equilibrium, heating balances cooling, but some energy can be horizontally taken away from location. And here I've just written in terms of a flux, basically. Right? So you do that, and you do this exactly the same procedure. And so you get the same, first two terms are exactly the same, but then you get this term, this mess down here. Okay? And this mess, it's quite a mess. And so we're trying to figure out basically how to model this in a lot of detail, linking this flux of energy via advection to fundamental jet properties that we were talking about earlier. And this is a work in progress. But in the meantime, I realized I could simplify this significantly. We rewrite this entire equation as basically this term and this term as the radiative term, and then this whole mess here as the advection term. Okay? So now I turn to my GCM models. I get that from my GCM models. I know how to calculate that analytically. So all I have to do is solve for T advection. That make sense? So that's what I've done. So again, all I do is I take the actual number from the GCM, subtract off the radiative solution, and I get the T advective to the fourth. Okay? So that's what I've plotted here. T advective to the fourth. This is pressure, so depth, and this is longitude. This is a slice at the equator. Okay, so this is high in the atmosphere, deep in the atmosphere. So the numbers are huge because it's temperature to the fourth, but you see red is positive, blue is negative. So that makes sense. Advection is a sink on the day side. It's taking energy away, and it's depositing on the night side. So that's great. So utilizing that, I basically parameterized that and came up with a model for a parameterization of that, which I can analytically calculate. Okay? So using what I've learned here, I analytically parameterized T advection to the fourth in this manner.
T is in some weird units, I imagine. I don't know what.
This T is in Kelvin, so but it's T to the fourth.
So you
So
have
it's huge.
things going from -4 10 power 3 to 1 10 power 13
Right.
fourth root of
The T itself is positive always. The actual temperature in the
Yeah.
planetary atmosphere is high. But the radiative temperature on the day side is so high that even though we're sucking away all this here, we still, this is negative there. It's this.
That's a
it's
huge
positive.
variation in temperature.
Yeah. So the nice thing about this is that I can play around with those parameters that I put into, I'm just showing you one particular simulation here, but I can play around with those parameters and I can create whatever jet I want. Okay? So I have this set of parameters I play, doesn't matter what they are here, this illustration that, here it's maybe a stronger deposition here versus a stronger deposition here versus a deposition that extends in a larger pressure range and so on and so forth. So we can create kind of, in this parameterized way, we can kind of create whatever jet I want.
So this is like, in your original language, this is like a data-driven or a retrieval for the jet property.
Exactly.
Yeah.
Yeah.
Good.
So the next step is to create a spectra, phase-dependent spectra, right? And so that just is a matter of convolving a visible area at a given phase. Okay, so I took this example is at 40 degrees. Again, this is latitude and longitude. Substellar point is here somewhere. Okay, so this is at 40 degrees. This is the region of the planet that I can see. Right, it's geometry, simple geometry. Okay, so what you do then is you calculate the flux. So you convolve the projected area with the temperature calculation based on this parameterization. So you have the temperature at every given pixel here, and so you convolve that with the projected area, and you get the flux from each cell. So with no advection, okay, here's what we get. So sorry, it's probably hard to see, but there's basically no flux here. This is the 90-degree terminator, right? So without advection, the only time you get energy is from on the day side. Night side contributes nothing. The same exact simulation here, but now including advection, all of a sudden you're actually getting a significant amount of flux on the day side. Sorry, on the night side at this particular point. So that is an example that just picked 4.5 microns. But of course you do this for the whole spectra, and you get the same following thing. So this is wavelength versus flux, again, emission flux. This is with no advection. So on the night side, when in phase is at, when you're seeing just the night side, you basically see nothing. But if you include advection, all of a sudden you can get a significant amount of flux at that value. So, to summarize there, we've developed a two-dimensional scheme. Again, I think it's the first two-dimensional scheme to generate phase-dependent spectra, where individual phases are actually coupled to each other and not independent. So the next step is to actually implement this in a full retrieval calculation in this kind of framework here. So we haven't actually run retrieval on this yet. But it's important to note that the goodness of fit of a particular model will be evaluated by looking at all phases simultaneously. So you don't just look at one at a time. You're looking at, you generate, say, 10 spectra all the way around the planet, and you compare all 10 of those simultaneously to come up with the goodness of fit when you're doing your exploration here. So I think it's exciting to think about this. One of the nice things is that this kind of 2D framework, as I've described it, will be able to incorporate some of these oddities. So this is something from Dang et al. We submitted in 2018. This is a snapshot, kind of picture of a bunch of hot Jupiters. They're rotating in this sense. So the hot spot on all these planets is offset in the eastward direction, or at least at the center maybe. But then all of a sudden we found these observations at Corot 2b where the hot spot's in the opposite direction. No one knows how to explain that. No model explains that. That's the only observation that happens. But that would be able to come out of this type of retrieval model.
But is it possible? I mean, the models, if you let them on their own, they naturally symmetry break in this one way. But if you give them a kick in the other direction, like my toilet also naturally symmetry breaks in one direction.
Yeah.
But if you give it a kick, it will go the other way. Is that possible here?
Yeah. So people have tried that. I've tried that to some extent. I haven't done a systematic study of that. But people
It's
have
expensive.
tried that.
You have to spend many
Yes.
weeks to find out.
Find that thing. People have tried that. It seems like everything eventually comes back to.
It does
It
come
does come
back
back
and
to
then
that.
flips.
Yeah.
Interesting.
I mean, that's also if these things were
It's
scattered
supposed
into
to
their
be that
positions.
Your toilet actually changes direction if you kick it. It's not very obvious to me.
Well, you might have to put a plunger in there.
Why are you guys keep talking about symmetry breaking? There is no symmetry. There is Coriolis fault.
I know.
I was going to ask Corey.
Well, just like with the toilet, there's no symmetry, but you can
But
get
it's
it
a
to go
little
down
bigger
either way.
than your toilet.
Yeah, that's
The
true.
Coriolis force it's there, but it's the rotational period is incredibly slow, right? The rotational period is 3 days.
Look, it's not that slow.
It's pretty slow
Much bigger
compared
than
to
the Earth.
Yeah, but
like,
I
say,
mean,
pressure.
so is Venus. It's rotation.
Yeah, but I think, people don't understand why Venus is so rotating.
But I mean, do you always get it to symmetry break in the direction that Coriolis force would predict? I was going to ask you this before.
Yes. Yeah.
I mean,
Like, that's what I'm saying. All simulations eventually predict either no offset or if any offset too. The jet is always in the eastward direction.
Does it have neighbors?
No. Oh, that's
He's alone.
a donor. Most hot Jupiters are.
Is there somebody using toilet on that planet?
No, but Dave is kicking.
I'm sorry. I'm sorry, and I'm not responsible for sure.
But you cannot see moons, right?
That's it.
I mean, can you? Or
What's that?
you know that this thing cannot have moons. Or do you-
Well, I mean, people are looking like crazy for moons, but haven't found them yet.
Would that
Could that explain the offset? No, I mean, this is a temperature induced, so no, probably not. Some ideas were, what if there's some weird cloud structures, right? If you have a weird cloud structure such that there's a hole right here, then you'd be looking much deeper into the planet. So that's one potential. Maybe this thing happens to be spinning the other way. Okay.
What about magnetic fields and fluxes? I mean,
Fluxes and
you're
things
laughing
like
because astrophysicists always say, "What about magnetic fields?" But,
Yeah.
but actually, this is pretty plausible that there would be a magnetic connection between the sun and the.
Yeah, so there's been suggestions that there's a flux tube basically between the surface of the star and the surface of the planet. You have to think about the geometry. Basically, there's a prediction about where you see a hot spot based on where the surface of this hits, but it's hitting the surface. Yeah. I don't think it works the right way because it's lagging. So it works the right way. Okay, so the other thing I was going to talk about, but I don't think we have much more time, is basically I told you about how important clouds are modeling. So we're actually now applying this to retrievals. And we have, and it's very interesting and great. Unfortunately, these complex microphysical cloud models seem to predict basically the same thing as very simplistic cloud models, where you just use a condensation curve, and every time the PT crosses a condensation curve, you put a cloud there. So these sophisticated cloud models don't seem to do much for you in these kinetic cloud models. In the retrievals, in one-dimensional retrievals. Okay. So I guess I'll stop there. It's 1 o'clock. So I think we're entering a whole new region in computational power where we can actually start combining these radiation hydrodynamical codes with all kinds of interesting physics. And all kinds of people are starting to work on all areas, magnetic fields, cloud formation, non-equilibrium chemistry, et cetera, et cetera. We're entering a regime where our data is going to improve immensely. I mean, people have done an amazing job with data so far in the planetary community, but the data is pretty ratty. So new models, I think, are really going to have to come along. Clouds are there. It's not really a question. But but we still really didn't understand that transition that I showed you from the clear to the cloudy. Why do some planets have a little clouds and some planets have a lot of clouds? So hopefully you understood this first multidimensional retrieval framework, which I think is pretty exciting. And once we have this, on top of that, we can put all kinds of other parameterizations, such as non-equilibrium chemistry and cloud physics, that really are able to explore this in a 2D sense. So I'll leave that there.
More questions? Can you say more about what the JWST observations are going to be? I mean, is it just better quality of the same, or is it fundamentally different observations?
What does abbreviation mean?
Okay, so
JWST.
Oh yeah, define
Space
JWST,
James
because we
Webb-
have people
sorry,
in the room who
James
don't know.
Webb Space Telescope. It's this 10-meter flying.
Which
What is
will
it?
sort of be the next generation of
I
Hubble.
know what it is.
Yeah, double this big. So these are synthetic. So this is synthetic data, but the black dots here are the synthetic data binned on the JWST kind of elements. That's Spitzer. 2 data points in that particular region, and that's Hubble down there. So JWST is going to extend across all this with incredibly high resolution. And like I said, yes, and basically, importantly, into the infrared. Whereas Hubble does great down here, but Spitzer points here. This is a huge light bucket here, which is collecting all the photons from here and tossing it at that one point. So we're losing all kinds of information there. So I don't know, what is it about now? 1.5 billion or something like that. Hopefully it'll fly next year.
So one thing I seem to remember about kind of these hot Jupiters that's puzzling is that they seem to be puffed up. Right?
Some of them are.
Yeah, so is that something you, as I missed the early part, is that something you were trying to also address, or is that...
Not with this stuff. I have been thinking about that for a long time. So I think the first thing to note is that some of them are puffed up, some of them are just fine, and some of them are kind of small. So there's a huge range. So these are all, when we say puffed up, it means based on the models that we've developed for Jupiter, can we apply those same models to hot Jupiters, or exoplanets, and explain their radii? And so there is a big problem with our understanding of some of these planets. They're basically way too big for what they should be. So somehow their interior interest, or their interior temperature, is much higher than it should be, given that it's 4.5 billion years and it should have been cooling this entire time. So there's a number of possible explanations for them, and no one really understands. But it's got to somehow, I think, be due to the interaction of this kind of wind layer with the convective interior. Most likely, or my best guess, is that winds in this atmosphere generate waves which propagate downwards, carrying energy with them, and they dissipate. And near the deeper down, then they can help puff it up. Other explanations, the original explanation was tidal forcing. So the idea is that somehow maybe they're not spin synchronized exactly, and so the tidal forcing associated with dragging that in would, again, keep them hot. But again, as I said earlier, the time scale for that to come into some equilibrium is very, very short compared to the age of the system. So we have to somehow have a mechanism of exciting the non-synchronicity somehow, which most of these planets are loners, and so there's not another planet perturbing it or something like that. So it's still an open question. People talk about magnetic fields. The problem is to simulate this, we're trying to simulate the upper atmosphere. We have Mach 1.5 winds with the down near the radiative convective boundary, where the radiative time scale is 10 billion years or 10,000 years. So in order to run a simulation that allows you to evolve for multiple radiative timescales near the radiative convective boundary while simultaneously running a simulation which is tracking the wind stuff, this is impossible. So somehow we have to figure out a way around that. So I think it's very exciting.
Have you done any work to try to parameterize either physical or computational effects from your 3D simulations in order to improve 1D simulations?
Numerical aspects, like resolution and things like that?
Yeah.
No, I haven't. But I'm not quite sure I understand where that would help. To understand how, I mean, the nice thing about one dimension is you can pump up your resolution to as much as you, no, not as much as you want, but a lot, and things like that. Or you can run over this range of parameters.
We may have certain instabilities in the 3D versions that are not present in the 1D versions.
Oh, for sure. Of the numerical instabilities, yeah. I was going to say there's also physical instabilities.
Right.
Yeah, I guess that's possible. Yeah.
Okay, so we're going to have a reception down on the 8th floor after this. And so let's thank you again.